So welcome to the day two of ABAQUS training. Uh, so from today onwards, the training will start. The real training will start with the ABAQUS. Now, Prithvi sir, you can start the session, sir.
Yeah, thank you.
You can present it.
So I hope you all can see my screen. Just a quick recap of what we have learned or what we have discussed yesterday. So yesterday we were discussing about the introduction of FE. We brushed through some topics on basics on FE. Then we tried to understand why we need to do this finite element analysis. So the major thing is, always the experiments are expensive to conduct. So finite elements also gives us some kind of an idea of how what you can expect from an analysis, and from there try to you can try to you can try to design your members or structures. Then we also learned about ABAQUS software, a brief introduction to the software. So major points which I want to highlight that we have covered yesterday is what are the inputs that you actually want to before you wanted to start modeling. So those inputs are again the cross section properties. First thing is that what is the cross section, or what is the span length of your beam. I hear anyone has any issues, any doubts, any, I think someone, yeah, Maheshwar, can you please mute your,
Yes, sir.
can you please mute because I hear some disturbance from your side.
Yes. Yes, sir.
If you have any doubt, you can unmute and you can ask me. Yeah, okay, thank you. So yeah, inputs again. What inputs we need is, we need cross section details. Then we need the material properties. We also need boundary conditions. These are the inputs that we require before we start our analysis or our modeling. Then meshing is again a part of finite elements. So we'll try to discretize the entire beam into different parts, and then we'll try to mesh it, and then we'll analyze it, and then we have visualization. So yesterday I got a feedback that my writing is not so it's not so clear. So I'll try to write. I'll try to do good job now. Maybe I'll try to do that. So pardon me for yesterday's writing. So fine. So this is the question which I wanted to solve for today's class. I mean today's tutorial. Uh, what we can do is like this is a very simple beam. You can see this is a simply supported beam, and what are the inputs that were given in this question is, if you see the beam is having, yeah, see, again, let us again think about this in, see, so what all do we have? So first thing is what all we want. Okay, so inputs, yeah, inputs, like I mentioned, cross section size or cross section details. There is some issue, I guess. Yeah, give me a minute. I hope it should work now. Is it not coming? There is some issue with my pad. So what I'll do is I'll just try to write it down here itself. Yeah. So first thing what we need is cross-section details. Okay. Next one is material properties. Third one is boundary condition. These are minimum basic things which we need, right? So let us check whether we have the same things given in this problem or not first. So in this, if you see, the problem is very simple. It is determine the reaction forces, bending moment diagram, or whatever, bending moment, shear force diagram, deflection profile of the beam shown in the figure using one-dimensional beam element. I hope you know what are one-dimensional beam elements, right? So see, there are actually there are different elements. First one is one-dimensional element, two-dimensional, three-dimensional. So in one-dimensional element, let us say this is a linear element. So this is one element. One element, you have a node, one node over here, another node over here. So what does the degrees of freedom does a beam element have? Okay. So degrees of freedom of this beam element will be having one translation in both the directions. It can have translation in both directions and it can have rotation in this direction. Okay. This is one dimensional beam element. So you have 3 degrees of freedom at each node. Okay. That's it. So you only consider the lateral loads in this case. So you have the lateral loads coming in this case. So out of plane, in plane loads. See what I when I say out of plane, this is nothing but in this direction. So it is into the beam direction. In this direction, you don't have any load. So it's only planar loads which you are considering. So you can have U1, you can have U2 as your degrees of freedom at one node 1, and U3 and U4 as degrees of freedom in node 2. Okay, and you can have rotation. You can have rotation at each nodes. So this is a one-dimensional beam element. Okay. Uh, okay. This first he's asking. He needs to. These are the outputs which we wanted to show from this exercise, and he's asking us to use one-dimensional beam elements. Okay, we'll see how we can use them. Then here, if you see this part, it has Young's modulus of 200 GPa. Any cases, or if Young's modulus of 200 GPa, what does that? What is that material? You can write in the chat box. I'll see it later. So Poisson's ratio of 0.3, and the section is circular. So section is circular with radius of 50 mm. So now what are the inputs that we want? First one is cross section details, that is given here. Second one is material properties. See, material properties they have given as Young's modulus, okay, and Poisson's ratio. So this is also given. Third one, boundary conditions. See, boundary conditions, again I just want to repeat it, so for the benefit of the class. So boundary conditions are nothing but what's happening at the supports. So you have, these are the boundaries. At the same time, even the loads are considered as the boundary, uh, the boundary conditions. So you have different kinds of loading coming on this part, which is AB, and there is one more load which is a point load at C. So can you quickly analyze this with your hand calculations and tell me what are the reaction forces? You can copy this question and you quickly analyze it, and you tell me, you can what all you need to tell me is, let us say this is my reaction force, vertical reaction force, at A and B, and yeah, I need only reaction forces. If you can draw bending moment diagram, I'm very happy. But for now, I need only reaction forces. Can you quickly solve this and tell me? I'll just clear this out. Hello, can you hear me now?
Yeah, yes.
Yeah, I don't know. Somehow I lost the connection. So
Now
I hope.
it's audible only, but
Okay.
you have to share your screen.
Yeah. Oh, it says I can't share the screen. Okay. I got one answer, which is RA is 53 and RB is 57. Yeah, it's always, it's always good to mention the units as well, because 53 kilonewtons and 57, I suppose. Okay. What about the others? 52.73, 57.27. Okay. Fine. Okay. Let us see. I think I'm not sure. I haven't solved that question. I think maybe that should be right. But fine. Okay. We'll go ahead now. So now we have these inputs. Like I mentioned, we have the cross-section details and we have the radius. So with the radius and also we have some material properties. Now, like I mentioned, this is a one-dimensional beam element. So let us start modeling it. Okay. So see, when I say modeling, it's nothing but I'm trying to replicate the dimensions over there. That's it. Okay. Modeling is nothing but you are trying to replicate your physical dimensions or whatever the given input dimensions into your software, and you're trying to give loads acting on it. You're trying to apply the boundary conditions which are coming onto that beam, and you're trying to analyze it. That's what the modeling means. Okay. So now let us start modeling it. So like I mentioned, this is how I'll just start a new model. So I'll go very slowly because I think no one is having this software installed, right? So I'll go slowly. So if you're not, so let me start from the beginning. So what I'll do is, even from the start of the software, I'll show it how it is done. So once you install, you'll get this app which is called ABAQUS CAE. You open that. Okay, it takes some time to open, so let's wait for it to open. So right now, create model database with standard explicit model. So I'll just click on that, and this is how the default graphical user interface looks like. Okay, GUI looks like. So right now, what I'm using is an ABAQUS version of 2019, but the one which we have shared to you is 2023 version. There's not much of difference between these versions, but yeah. Anyways, in first and foremost is like you need to set the directory. So where this has to save. So go to this tab, which is Files tab. First set work directory. Okay, go to set work directory. So right now it is being by default it is going to be saved in this C drive, but I don't want it to be saved in C drive. That's again my own, like everyone has their own personal choices. So I have this folder I want to save in this folder. Fine. So in this folder it is going to save. Now I should also give some file name, right? So what I'll say is save. I'll say day one. Day one will be my file name. Okay, now everything is set, right? So file name is also being saved now. So if you remember the process, first one is creating the geometry. Second one is assigning the material properties. Third one is boundary conditions. Fourth one is meshing. Fifth one is setting up the type of analysis, and then running the analysis. Okay, that's a major. So now let us go back to the question. So what does the question says is, the question says that this is a beam of 50 mm in radius. So what I'll do is, in this module, you see this module part, in the part, go to this this icon which says create part. So in this part is nothing but the member which you are going to design or member which you are going to analyze. So create part, then this thing pops up. You can see this window popping up. I can name it. So now I want to name it as 1D. Okay, maybe initially it will not take numericals. So what we can do is I will say one dimensional beam. One dimensional beam. Okay. So modeling space, again, this is a one dimensional beam. So the modeling space is 2D planar. It's not a 3D. So this I'm only modeling it as a 1D element, right? So this is 2D planar. And it is deformable. It can be rigid also. What does rigid means? Rigid means whatever force you are going to exert, it is not going to deform. That's what the definition of rigid means, right? but in our case, the beam has to deform. So it is a deformable. And base feature, shell, point, and wire. I'll tell you what wire means. So for now, you select this wire, and approximate size you can give. I'll also again explain about this approximate size, but this is, let us say, 2000. Okay, now you will get this grid. So I think you are able to recall your AutoCAD sessions, right? In AutoCAD, you will also get something like this, grids and all. So this is again a sketching interface. So here you can sketch it. So you can create the geometry. So if you remember, I was giving something called 2000 over there, right? It's nothing but this length is 2000 by 2000. That's it. So if you have a bigger length, you give some 10,000 over there. Okay, that has nothing to do over here. It's only that you just want to work in 2000 by 2000 kind of a grid. So let us start first. So now I want to create a beam element. Okay, I want to create a beam which is a linear element, 1D dimension, one dimensional beam element. So now, what are the critical, or what are the major points? So one is this point, another one is this, because this is where you have UDL acting. Another point is this point, and another point is this point. Okay. So these four are the nodes which I want to create first. Fine. So these are the points which I want to create first. So what are the coordinates of this point in XY plane? So this is XY. Similar to AutoCAD again. So in XY plane, what are these coordinates? I'll take this as 0, 0 first. Then this is going to be 3000, 0. And what about C? C is going to be 4500, 0. And D is going to be 5500, 0. First, I'll try to establish these 4 points, 1, 2, 3, 4 points, by giving those nodal coordinates. So what I'll do, sorry. So here you have several several tools where you can use them to sketch or model, or draw your beam or member. So this is nothing but you can create an isolated point. First, I want to create an isolated point. Then I want to join those points to make a line. It's like, again, it's similar to your AutoCAD Stat Pro, where you will initially create nodes and then you'll join it, right? So first I am trying to create this. I'll first click on this. Then you can see here, pick a point or enter X, Y. So first point is 0, 0. What is my second point? Second point is 3000, 0. 3000, 0. Third point is 4500, 0. Fourth point is 5500, 0. See, I missed one point, actually, one important point. See, yesterday, if you remember, I was telling that ABAQUS is, see, in ABAQUS, there is, see, nowhere I have considered any kind of units, right? I never set up some units on this, right? So ABAQUS, you need to be unit consistent. So initially, if I start assuming that I want to give all the dimensions in terms of millimeters, then corresponding forces, stresses, everything has to be in kinds of your millimeters. Like, for example, if you want to start with length as a millimeter and your force as Newton, then your stress has to be incorporated as Newton per millimeter square. Okay. And even if you're, for example, even the loads, when the loads are acting, if the loads, let us say it's 50 kilonewtons, but you have to input it as 50,000 newtons, because you started assuming that you wanted to give all the units in terms of newtons, millimeters. I think, yeah, newtons and millimeters are your forces, as well as your length, or the length dimensions. So here I am using millimeters, so that's the reason why I have given this in terms of all the nodes in terms of millimeters. So see, now you can see 1, 2, 3, 4. These are the 4 points, and now I'll join those points using this icon over here, which is create lines connected. So I'll join these points. I'll join here and I'll join here. Okay. Now I'm done. I got these lines. 1, 2, 3. 3 lines I've joined using these 4 points. So now I have given a line element, and now I'll say done. Now I have created this line element. Okay. So so now I have only given the span details. Okay, this is span details, right? I have so far I haven't given the cross-sectional details yet onto this beam. I just drawn a line, something like this, and then I have given those details of salient points on this beam. Next part is property. Okay, next I'll go to property. Like I mentioned, now in property, first let us assign a section. So before assigning a section, let us create material, or let us uh, input the material properties of this beam. So again, similar to your previous module, which is part. Now for this is previous module, which is part. Now the next module is property. So now in property, you go to the property. So you'll have these icons displayed. Go to this icon, create material, press onto that icon. You can again name it. As I think some others are mentioning, it is a steel. Yes, it's steel. So I just named it as steel. So you see these many what do you call sub tabs over here. So what I'll do is I'll go to this mechanical, I'll click it. So elasticity, I'll go to elasticity and I'll click this elastic. When I say elastic, these things pops up. So Young's modulus. So now I want your response. So what is the Young's modulus given in this question? It is 200 GPa. So what should I input here? What should I input here?
200 into
I
10.3.
200 into 10.3. Yes, yeah. Yes, Mahesh. It is like STAD or ETAB. Yes, it's similar to that. But later on you'll see some differences. But yes, it's almost similar when you're sketching it. When you're trying to uh, sketch model it, it's almost similar. So 200 into 10.3. Yes, you are right. So 200 into 10 to the power 3. So what I'll do is I'll add another 3 zero. So this is 2. Yeah, it's 2e5. So or 2 into 10 to the power 5. Whatever. Poisson's ratio is 0.3. Okay. So now I have given it. Now I'll say okay. Fine. So now material properties are also given to this line. Still, I don't want to call this as a beam because it's just simply a line element over here. Now I'll actually try to assign the material cross-section properties. To assign the cross-section properties on this, what I'll do is I'll create a section. So here again, this is a tab where you want to create a section. So what I'll do here is I'll say that I can name it circular. Now category, it's a beam. It's a beam element. So it's a beam. We'll come to these things later. Not for today. You only think about this one. You only see this part, which is beam. So in beam also you'll have truss elements and beam elements. So now I have a question to you all. What is a truss element and what is a beam element? What are the difference between those? Truss and a beam element. Uh, in truss element, one typical there's a one major difference between these two elements. So truss elements and beam elements. Truss elements only has axial forces. Yeah. What about beam elements? Can someone else answer? What about beam elements? Beam elements can carry shear force and bending moment. Shear force and bending moment. Yeah. Beam elements designed to resist lateral loads. Yes, yeah, with negligible axial forces. No, Raghu, actually, beam elements can also have axial forces. Only that we are dealing with two-dimensional things. There we don't consider the axial forces, but yes, beams also have axial forces. Uh, See, in this only I was mentioning, right? So if you remember, okay, I might see when you have this part. Let us say this is a beam element. I think others are right. So like it can take lateral loads. Yes, that's true. So this is 1 degree of freedom. This is another degree of freedom. So usually I call it as u1 u2, and this is theta 1, and you also have u3 and u4, and this is theta 2. So let us say you are trying to apply. See, in simple case, let us say it is a fixed beam, and you have some elongated portion over here, and you are applying lateral load in this direction instead of your typical this direction. I want to apply lateral load in this direction. So if in this direction, what happens? So let us, in this case, what happens is that the forces also transfers in this. I'm just doing a force translation and moment translation. So you have forces at this part, and this will be acting here again, and because of this, you will get some moment over here. So because of this force, it is going to resist these um, axial forces also. So beams will also take axial forces. Only that we are mostly dealing with these problems where only lateral loads are coming. That's why usually we'll neglect. Yeah. Anyways, in this case, there's no axial loads which the beam is going to carry, because all the loads are actually perpendicular to the beam's longitudinal axis. So that's why there is no lateral or axial forces coming in this beam. But yes, beams will also take axial forces. So what are the other answers? I just want to check. Horizontal reaction forces will be produced which are axial in nature. Yeah, okay. Shivakumar said beam elements designed to resist lateral loads. Yes, beam carries flexure and shear force. Yeah. Yes, yeah. Okay. Thank you. So yeah, so most of you are right. So this is a beam element. So that what I wanted to design is a beam element. So for a beam element, it has to carry bending moments. So that's why I have considered the type as beam over here. You can see here, it is a beam element over here. Now, okay, maybe you might have forgot what we have done. I'll just again recreate again. So create section, beam. Section is a circular section. Continue. Profile name. So now what I'll do is I'll see you have this create beam profile. So what is the cross section given? The cross section given is a circular beam with 50 mm radius. So I'll just click on to this, and you'll get different cross sections over here. So I'll create uh, uh, I'll select the shape as circular, and then I'll say continue. So now you will get this window popped up. Most of you, I think, you are able to relate this to your stat, but yes, yeah. So R, what R should I give? What is given in the question? The question, what is given, and what should I consider now? 50, correct? Yeah, because we are considering in terms of mm, so it is 50. So R is 50. Material, if you remember material, we have already defined our material properties, which is steel. So it's by default, it is already taken here. Section Poisson's ratio is 0.3. Okay, these things are default. You say okay. Now section is created. Okay, so now in this what happens is that, again similar to your stat pro again or etabs, the section which is created, you have to assign it to the beam or assign it to the elements which you have already modeled. So there is this tab which is called assign section. Once you click onto this, you need to completely select this part. It will also create your sets. That's okay. You say done. It will ask you, see, for example, if you have multiple sections, then it will give you multiple. Uh, when you select this, you will get a drop down with several other sections, but in our case we have only circular section, right? So I'm just saying circular, and then I'll say okay. Now the section is created. Now the major thing in the beams or one-dimensional elements is you should also know the orientation of the beam. Okay, see here it is a circular beam, so orientation doesn't matter. So when I say orientation, what I mean is, I'll just show it here. When I say orientation, see now I'm taking a rectangular beam. So this is, so if I want to use this beam as a beam element, or as a, sorry, if I want to use this cross section as a beam element, which orientation should I consider? One or two? Sorry, yeah, you can see this. Which orientation should I consider? One or two? If one y, if two y. Can you please answer? Sure. So if, again I'll repeat my question. You have two different orientations, 1 and 2. If you want to consider, if you want to select one of these sections as a beam, which will use which orientation will you consider? And if you're selecting one, y, and if you're selecting two, y. One has more moment of resistance than two. More moment of resistance. So moment of resistance, moment of resistance. So see, moment of resistance, I don't think so. Why do you think moment of resistance is? What if the other one is having higher reinforced? If you, is it moment of resistance or moment of inertia? Second moment. No moment of inertia. Okay. What about others? Yeah, fine. So one, definitely will be choosing one over two. But see, in your cross section, let us say if you have defined something like this, and if you want to, okay, now you need to actually define the orientation also of this, right? So you need to when you're assigning this to a small like this line element, then you need to define the orientation of this beam to this element to this line also. So for that we need to do an orientation. We need to also set an orientation in ABAQUS. I think we'll be doing the same thing in STAT also. So for doing that orientation, beam orientation, you need to click onto this, and again you select the entire beam. Say done. See now what it is trying to tell you is, this is the longitudinal axis of your beam, and it is oriented in this direction. So because luckily this is a circular specimen, so for circular specimen the orientation doesn't matter, because it is symmetric in all degrees. Yeah, sorry, symmetric in all planes, right? So what I'll do is I'll just say okay, and you can see this orientation coming up, popping up like this. So now I have also oriented the beam. So what is my next step? Now I have completed my sketching. Second part, I have input the material properties. I've also oriented it now, and my next step is would be load definitions, right? Boundary conditions. So before that, we need to do an assembly. So
Sir, can you repeat the orientation part once again?
yes, yeah. So let us say if we have instead of a circle.
In the model, sir, in the software.
Sure, sure. So this is this is the tab, or this is the icon where you need to assign beam orientation. So you click onto this beam orientation, then you select your beam, entire beam. This is your beam, and you just press done. So here you see the tangents are given here. Enter an approximate n1 direction tangent as shown in this. So this is already given. So this is in this direction, which is uh, in terms of minus x. So it is facing in this direction, and then press enter. So you'll get this one, 1 and 2. Fine, you have oriented your beam in this direction. So the cross section, see, the cross section is actually like this. So let us say your cross section is like this, and the beam is in this direction. So it is in this tangential direction. This is your 1, and this is your 2. Okay.
Okay, sir.
So you press OK once it is done. The next step is, see, I think I have, yeah. The next step is assembly. This I was not talking about. This part I was not talking yesterday because I think yesterday if I speak about this, I think it will not be so clear. So in assembly, what will the reason we are doing is, so initially, let us say in our case we have only one beam, right? So what if you have several elements? Okay, like let us say if you want to model one beam like this and also one column like this. Okay, so what we'll do is we'll make two parts. Part 1, this will be part 1, this will be part 2. So you can do both things with as a different parts, two different parts, and then you can assemble it in this assembly. Okay, in this assembly you can bring it back, bring it both the parts here, and then you can assemble it. But right now we have only one, so that's why I'm just using that one. So what I'll do is I'll go to this tab which is called create instance. I'll click onto this create instance, and the parts which I have created is one dimensional beam which I have created, right? So there I'll select that and then I'll click OK. For example, if we have some other parts also, like I mentioned, if I have column also in this, then two will be highlighting here, one beam and also column. Then I'll select both of them and I'll say OK. Then two parts will be coming here. So for today's case, we have only one beam, so only one part came up. Then I'll go to yeah, we have done with step assembly. Then we'll go to this part, this module step. In step, we'll be defining the type of analysis. If you remember yesterday, what are the two types of analysis we have? One is not like we have several analysis, but we have discussed only two types. One is static. We have another one is dynamic. So in today's case, we wanted to do a static analysis. So again, you open this this create step, say create initial static general. I'll say continue static general. It's already by default it's used. I'll say continue. Now yesterday I was talking about, if you remember, I was talking about non-linear geometry. NL-geom is nothing but non-linear geometry. Okay, so here I just want to include non-linear geometric effects. yesterday, if you remember, in all our basic courses, in all our mostly undergraduate courses, what we'll assume is the deflections or the deformations are very small. And when we say very small, then we are not considering the nonlinear geometry in our analysis. But once we have a higher computational, this is a computational software. So why we should still hang on to that assumption? Let us switch on this nonlinear geometry. So I want to switch it on here. Time period, you keep it as 1. And next one is incrementation, probe incrementation. Here you can set up increments. So this, like yesterday I was mentioning, right, Newton-Raphson scheme. So it keeps on iterating its results. So whenever you say a number of increments and all, these all comes under your iteration scheme. So for now, I'm just giving it as 10,000 or 1 lakh, and my initial increment size is 0.01. Don't worry about this for now. Okay, this is like for now. You just try to enter these values. When you keep on analyzing, when you keep on understanding different models, you'll understand the role played by these figures here. For now, you just follow these things. What I'm doing right here. So then press OK. So now this is created. Step 1. Procedure is general, static general. I have switched on the nonlinear geometry and time is 1. And now I'll close this. Okay. Now I have also defined the step. Next part will be boundary conditions. So boundary conditions, you can give it using this load module. So far, any doubts? Any doubts, or you are able to follow? Raghu, you have this software installed, right? Are you able to follow what I'm doing?
Yes, bro. Yes, bro. I can able to follow.
Okay. What others? Do you have any doubts or queries? Okay, I'll ask. No doubts. Okay. Yeah, that's a very good way of telling, because Shiva was saying no, sir. So no, sir is for are you able to follow, or no, sir is for do you have any doubts? No doubts. Okay, fine. Thank you. Okay, all right. So I'll just continue. Uh, in this module, load module, like I mentioned, uh, so again, I'll just repeat. So we have done sketching, we have created the cross section. Second one is we have given a material property. Third one is we have assigned the cross section. We have assembled the section. We have in step we have provided the type of analysis, which is general static. Next, we are coming to boundary conditions here. So in boundary conditions, now I think it's your turn to tell me what boundary conditions we need to apply. So first I'll show you what are actually present. So this is a create boundary condition module. So now I'll apply this. I'll switch on to this, and here I'll say support A, just for our convenience. Support A name. So name I can give it a support A. You have mechanical, electrical, magnetic, others. Right now we'll not worry about these two things. Mechanical is what we are worrying about. And displacement rotation. So these are the deformation boundary conditions, or displacement boundary conditions. Displacement or rotation, which is a kinematic degree of freedom, right? So I'll try to switch on to this displacement rotation, and I'll say continue. Okay, now when I say continue, now tell me where are my boundary conditions. One support A and one in support D. So support A, I'll just apply select that support, and I'll say done. Now you will get this window popping up. U1, U2, UR3. I'll just explain what is U1, U2, UR3 here now. Yeah. So what is U1? Now we have the support A. Yeah. Assume this as a straight beam. So this is one support, this is another support. You have UDL load coming like this, and you have, okay, this is support A. Support A is a pin support, and support B is a roller support. This UDL is 20 kilonewton per meter, and this is 50 kilonewton. So A, B, I think this is C and D, I guess. So now in support A, what was asked in what was popped up? So here it is asking U1, U2, and UR3. So when it says U1, what it means is this part. So if it is support A, this is U1, this is U2, and this is UR3. Okay. Now tell me, in support A, what are see? Okay, I'll just tell you one. U1, U2, UR3. Now in support A, what will be my U1? What will be my U2? U1 is nothing but displacements at support A, okay, in X direction, and U2 is displacements in Y direction. Okay, so can my support A can it have a displacement in X direction and Y direction? Is it like STAD or DTAB? U1 should be 0 and U2 should be 0. Yes. Yeah. Can it have? What about UR3? Can it have rotation? Yes, it can have rotation. Yeah. So U1 is equal to 0, U2 is equal to 0, but UR3 cannot be equal to 0 because it can have some rotation. So that's what we need to mention here. So I'll click on this U1, I'll say 0, U2 it is 0, but UR3 I'll not click it because I want it to have some finite rotation there. Okay, and then I'll say okay. Now my next, what is my next boundary condition? Next boundary condition is over here. Maheshwar, actually he was, I just missed you. It is like STAD or ETAB. So it is like STAD or ETAB, but this is a very basic model which I'm trying to explain. But I'll tell you, like, in coming classes, I think we'll try to see RCC design. There you will appreciate more about this software. So just as a this is just as a basic, basic, because you are I know that you are all comfortable with the STAD and ETABs. That's why I just picked up a very small beam here, and then I'm trying to show it to you so that you will understand, what are the relations between these two. But we'll see some things, we'll see some things where we can't see such kind of things in STAD and ETABs also. Okay, but yeah, you are right. It is almost it is similar to STAD or ETAB. Yeah. So boundary condition 2, I'll again name it as support B. Support B, and if you remember that my support B is somewhere here, right? So here I'll say done. Now tell me in support B what should Raghu, this time you can just you can, okay, you already messaged only U2 equal 0 at B for general loading. U2 equal to 0 at B for general loading. Yeah. What about rotation? Rotation is there. It will be there. Yes. So yeah, U2 should be 0 because in my support B, if you see, this is support B. Here, this is U1 and this is U2. So my support B doesn't allow the beam to move in this direction, right? Up and down. So my U2 is 0, but U1 cannot be 0 because it's a roller. So it can slide. Here you can it is free to slide here. So u1 is not 0, and obviously it will also allow rotations here. You will also have some rotations. So ur3 is not 0. I'll say okay, press. I'll just show it as this one. Next, we need to assign the loads. Okay, to assign the loads, I'll go to this module, this tab. You can see this icon, create load. If you see in create load, you have a body force, concentrated force, moment, pressure, all these things. So I'll select line load because first part is my line load, and I'll say continue. And now I'll select the part where I want to uh, load my beam. Then I'll say done. You'll get again component 1 and component 2. So always remember your component 1 is in x direction. So you can see this is your global coordinates. So component 1 is in global x direction, component 2 is global y direction. So now tell me, what is there any load coming in x direction? There's no load, so I'll say 0. You can just keep it blank also, but I'm just saying it as 0. Component 2, tell me now what should I enter for component 2? The given load is 20 kilonewton per meter. So what should I enter for component 2? 20 Newton per mm. Is it practical purpose for designing? See, this is actually not a designing software. Uh, this is more likely an analytical software. Yes, yeah, 20 Newton per mm is right. Yeah. So instead, like I mentioned yesterday, I was mentioning you, right? So if you want to know how the cracks are propagating, if you want to know how your beam is going to behave in different kind of loading scenarios, when you have impact, blast, different kinds of loads, sometimes thermal loads, even earthquake loads. And if you want to see a component, like for example, if you have one simple component and you want to see how that component is behaving in different kind of loading scenarios, then we'll use this. Again, I know that you are maybe you are thinking that it's almost similar to stat, but just have some patience. So we'll try to do some critical or some kind of a not very advanced, but some advanced things in coming classes. So there you will try to appreciate what we are trying to do with ABAQUS. Okay. So yeah, this is 20 kilonewtons. So I think you guys are able to follow now. The reason why it's newtons per because 20 kilonewtons, so we want to use it in newtons, and meters it's not in meters, so mm. So yeah, it's 20. So now it's not actually 20, it should be minus 20 because it should act downwards. Now I'll say plus, so this will show up. Next one is my point load. So I'll go to this concentrated again. I'll select this part, create load, concentrated force. Then I'll select this node and I'll say done. And here again CF1 and CF2. So what should be my CF2? CF2, how much is my CF2? 50 kilonewtons. So instead of 50, I'll be adding minus 50,000 because my nodes my units has to be consistent. Now we are done with our loads. We are done with our boundary conditions. Next step will be the mesh. Okay, so next I'll go to this module mesh. Now I'll mesh it. What I'll do is I can create this seed part. So you need to. The reason why you can see here this thing this dialog box has popped up. It says that dependent part instances cannot be edited or assigned mesh attributes. Try the operation on associated part or select make independent. So see what it's saying is object, you can't do an assembly, entire assembly as a mesh. So you can just go to a part and now you can select. Okay. So now this object I have, what I have done is I have just selected this part and then I have selected this. So now this dialog box has popped up. This now what it's saying is approximate global size is 300. So right now my entire beam, what is span of the beam? Span of the beam is I think 5,500. So it can create three mesh. It can discretize this beam. It can break down this beam into n parts with each part having 300 mm element length. Okay. So I can go with 300. I can go with 500. So Raghu, what I want you to do is you can uh, we'll see how the mesh size actually varies. So only Raghu is having software with him right now. So what I'll ask is Raghu, you can give this approximate global mesh size as maybe 1,000. Okay, you can give it as 1,000, and I'll give it as 300. So we can compare our results, and we'll also see why the mesh size is mattering. Okay, so I'll take it as 300, and Raghu, I think Raghu will be taking it as 1,000. Is it fine, Raghu?
Ah, bro,
You didn't follow. You did not model it.
yeah, bro. Just
Okay, fine. Then leave it. Okay,
okay,
fine.
okay.
So approximate global size, I'm giving it as 300 in my case.
Sir, I have
Uh,
modeled it, sir. I'll take it as
oh,
1000.
who's this?
Burhan, sir.
Burhan. Yeah, Burhan. You can take it as 1,000. We'll see.
Okay, sir.
You are able to follow me, right? So far.
Yes, sir. Yes, sir.
Okay. Okay. Great. Okay. You can take it as 1,000. We'll see how our results are varying. Okay. We'll compare. Yeah. So I'm taking it as 3,000, and Burhan will be taking it as 1,000. And I'm clicking it on OK. I'll say OK. See, now it has discretized. So entire beam is now broken down into these many parts. So each part actually is 300 long, and maybe some parts are slightly lesser because 5,500 by 3 you will not get an integer. So that's why maybe the one part should be slightly lesser. So anyways, this now I have meshed it. This is my meshing. Now I'll say OK, and then I'll go to this part which is called mesh part, and then I'll say OK to mesh part. Yes. So now you can see some breakdowns on this. Maybe the resolution might not be so good that you are able to see it, but you can see some beam broken down into parts here. So once the mesh is done, Burhan, you are able to mesh it, right?
Yes, sir. Yes.
Okay. So once it is meshed, next step is, see now I think we are done with most of our modeling. So now to visualize the results, we should also see. We should also give what are the results which we wanted to see also in this. We can also, anyways, we can always keep ask. We can always query all the results which we want. But if you want to query all the results which you want, it takes a lot of time to compute. So in our case, we only want moment, bending moments, shear force, and deformations and all right. So what we'll do is uh, we'll just query only those results. So to query those results, what we need to do is you go to this. So this is called model tree. I forgot to mention. So on the left side, you see this is a model one. You have part, material, calibrations, sections, profiles, assembly, all these things, and you can see field output requests. So here you can request what results you wanted to see in your final results. I mean final visualization. So go to this tree, F output. You you do a right. You make a right click here. Then you go to edit. See, it already has these things. Let it be. You create a new one now. You go to this, you say create f output. Let the name be this f output, whatever the default of. Say continue. Okay, this is continue. Now go to your, like, what do you want? You want forces and reactions, right? So you see forces and reactions over here. Uh, Again, for the benefit of everyone, I'm just saying you can query different types of stresses, strains, displacement, velocities, accelerations as well, forces, reactions, contacts also. Like, when you have this impact happening, you can also say what will be the contact forces in that. Energies also in this. Failure and fracture. Thermal. Thermal means, like, you can also see nodal temperatures, heat flux, time integrated on all these things. Electrical, magnetic, anyways, we are not worried about these things much. Volume and thickness coordinates, error indicators, state, field, user. So all these things, I think these things are, all the other extra things are not available in STAT. See, for example, in energy, you can't do it in STAT. Contacts cannot be done in STAT. Failure and fracture cannot be done in STAT. Thermal, electrical, porous, volume, thickness, error indicators. So these are for the finite elements. Mostly these are used for the finite element processing, for processing the finite element models. So yeah, coming back, we need to select these forces, and in forces you have reaction forces, moments, reaction forces, reaction moments, etc. So you select this N force core. Okay, nodal forces in beam section orientation. Okay, at each node, what are your forces? You can select this part and you say okay. I'm just repeating forces, reactions. You just maximize this, go to enforce go, you select this and say okay. Now you have given your field output. Now go back. Now I think the things are ready now. We'll go to job. So to run the analysis here, instead of going for stat, usually you might be going to run analysis, but here we'll be going to job. Again, in module job, you have a create job. First you will create a job. This is 1D beam, right? One dimensional beam. I'm giving it as one dimensional beam. Name, continue. Everything, it can be by default, and then say okay. I'll also talk about parallelization, but right now I think this is not a very hard job. I mean, not a very computationally, it will not expensive one. So let it be. All the options will be by default, and go to say okay. And once you say okay, the job will be created. You can see here the job has been created. Then go to this job manager. Then the ones which you have just created. Go to this and say submit. Now I have submitted it. I think now it's running. Hopefully I should not have any errors. If we are lucky, we'll get some errors. So if we are getting errors, then I can also tell you why that error is coming, and then we can troubleshoot. If we are not lucky, then we'll not get any errors. Yeah, I think we are not lucky. So the analysis is done now. I did not get any errors. Burhan, you got any errors?
No, sir, the job is completed.
Oh,
Status.
okay, excellent. Okay, good. So now the status is completed. Now what I'll do is I'll go to this results and I will click on those results. Now you see this is a visualization module. Visualization. Sorry. So when you see this, right, what are the differences? This is a initial undeformed shape. This is a deformed shape, and this is a contour shape. So you just press on this, you see the deflections. So first one is here you can see this tab. Here it is showing it as S minus S. S is nothing but the stresses. Mises is nothing but the von Mises stresses. So let us see only the deformations first. So you can just click this drop down and you see deformations. So in my case, the deformations are as high as 2.28 E02. That means 228.6 mm. What about you, Burhan? How much is it in your case?
So how did you
You
change that SS
Yeah, yeah,
to magnitude?
sure. You can check this. So this part. Initially, I think you're getting this S Mises.
Yes, sir. Actually, it's placed in other directions, so I was confused.
Okay. So can you check this U now?
Yes, sir. I got it.
How much is it?
2.263 E plus 02.
2.26. Yeah. See, for me it is 2.228.6, and I think for Burhan it is 226. Right. Let me just note your values down. So Burhan, what's your element size? 1000, right?
No, sir. Actually, I took 500, sir.
Oh, you took 500. Burhan's element size is 500 and my element size is 300. So let us say deformations. I was getting 228 mm roughly, and Burhan, you're getting 226.
Yes, sir. 226.
Yeah. What about the stresses? Go to S Mises and check your maximum. I'm getting about 698.2.
688.7. 688.
698, 688. These are S Mises. And let us check your longitudinal stresses. Longitudinal stresses is in this direction, in X direction. So that will be S11. So S11, I think it should be the same, right? How much you are getting? S11.
Same, sir. Same.
S11 is also same. So I'll just mention it here. S Mises and S11. So this is one part. Next, what? Just we'll get back to this again. Now we want to, and then what we wanted to do, we wanted to get a bending moment diagram, and we also wanted to draw a shear force diagram. So to want to do all those things, what we need to do is, there is something called path over here. Path, you can see on the left hand side there's some path. So first thing is we need to define the path. So bending moment diagram has to start from here, and then it has to go all the way along this beam, and then it has to end at this end, right? So I need to give that path to the abacus to say that, you from this along this path give me the shear forces, so that I'll get a shear force diagram. Along this path give me moments at each node, so that I can draw a bending moment, so that I can draw a bending moment diagram. So first, for that we need to define the path. First, let us go to this path and say create path. Now it will ask you the path, which kind of a path you want: node list, point list, edge list, or circular. So we'll go with a node list. I'll say continue. Now here, if you see, it is asking me node labels. So node labels is nothing but you have several nodes along this path, but we don't know what are the names of those nodes. namespace, like the nodes will be labeled as 1, 2, 3, 4, something like that. So we don't know what are the names of these nodes. So in order to know the names of those nodes, what we can do is, let us go back to this module and let us go to this mesh. I'm just repeating again. Let us go. We want to find out the names of these nodes. We'll go to this module. We'll go to mesh, and on the top you can see there is this view option. View. I'll click this view. You can see here part display options. Go to this part display options. Then you'll have this dialog box popping up. Burhan, you are able to follow?
Yes, sir.
Okay. Then I'll go to this tab, mesh tab. So here it says show node labels. So I'll just say show node labels and then I'll apply. Now I can see the names of my nodes. So it is like 1, 5, 6, 7, 8, 9, 10, so on and so forth, up to 13. And then I think what is this is 2, 14, 15, 16, 17, 3, 18, 19, 4. So this is actually slightly weird, but what I can do is I can note it down 1 to 5. I'll try to note it down. Now it is something like this. My Burhan, you can also have different node labels, but I'm just not noting down I'm noting it down what I have. 1 comma 5, then 5, 6, 5 to 13 it's ascending, right, with one interval. So 5 to 13, then I have 2 here, and then 14, 15, 16, 17. So after 2 I have 14 to 17, then I have 3, then I have 18, 19 and 4. 18, 19 and 4. Okay, Burhan, you are able to write your things down, notes down.
Yes, sir. Yes.
Yeah, can you just show me? You otherwise it's okay. That's fine. I think that's okay. So these are my notes: 1, 15, 5 to 13 to 14. So what I'll do is I'll input these node into my path now. So again I'll go back to my path definition. So where if you remember, I'm giving my path definition in visualization module. So module visualization paths. You can see on the left you have this path. Right click, create, node list, continue. Now here what I'll do is 1, 5. So 5 to 13. Don't give any spaces actually. There is no space, I guess. 1, 5, 5 to 13. Then 2, 14 to 17. 2, 14 to 17. Then 3, 18, 19, 4. 3, 18, 19. Okay, so now I have given along this path. See, the reason why I'm giving this in this sequence is, let us say, if I'm giving it as in 1, 2, 3 kind of an order, like say 1 to 19 directly, what happens is that it will take 1 here, and where is my 3? 3, my 3 somewhere over here. So my next point will be 3 here, and then again it comes back, and again it goes back here. So when I'm drawing my BMD, I'll not get along this path. I'll get 1 over here, and then this part here, and then all these things here. So that's why I'm giving it in a sequential order here. Okay. So 1, this is my sequence. Burhan will have his own sequence. So I'm pressing it OK. So my sequence is done. Now I want to extract my bending moment and shear force from this. So I'll for that what I'll do is I'll go to this XY data, right click, say create. Now I create a path, say continue. See, my path is actually you can see it is highlighted here. Now this is path. Now you say field output. If you remember, previously we are giving field output, right? We gave this N4 score over there, right? So you click on this field output and you see here these things popping up. When it says M4 score 1, nodal force in beam section orientation at element loads. And N4 score 2 is nodal forces in beam section orientation at element nodes again. So this is nodal forces in direction 2. So in direction 2 is nothing but shear force. It's a shear force in our beam. So first you select this 2 and say apply, say OK, and say plot. So this is my shear force diagram. Burhan, what about your diagram?
It's similar to it, sir.
Yeah, no, can you tell me the values? Okay, for the values, what we'll do is if you want to check the values over here, right? So this is the plotting actually. This is how your plots look like here. So if you want to see the values, so right now if I even keep my cursor here, I'm not able to see the values, right? So what I'll do is I'll go to this tools, query, I'll say probe values. I'll click that and then I'll just minimize it here. And this is my 49.3 kilonewtons over here. And at this it is 56.76, 49.3. And what are your values?
Sir, it's 56.78.
And at A, first point?
47.3.
Okay. So your forces are lesser, right? I think your forces are slightly lesser. And by your hand calculations, how much you are able to get? I think initially you gave 52 and 57. And others, what did you say? 53 and 54. Okay. See, you are able to get this 49.3 and here it is 46.76, right? And this is about the shear force diagram. So shear force is something like this. It goes down here and it goes linearly. No, it doesn't goes linearly. It is kind of a parabolic function here because you have a UDL in this span, and then it is constant because there is no load in this span from 3 meters to 4 meters. And from 4 meters onwards you will have again a linear one because at 4 meters you have a vertical force acting, so you have something like this, and then after this you have a reaction force at this support. Now you understand when you are analyzing the other parts, right? So if you keep on increasing, so for Burhan the values are slightly different and for me the values are different. So now you should understand one thing, that these results are highly mesh size sensitive. If your mesh size is different, then your results are going to be different. Okay, so that thing you need to understand. Also you need to highlight. So your mesh size or your mesh is going to play a very vital part here. So let us also see the bending moment diagram also. Again, for the bending moment diagram, what we'll do is similarly we'll go to this XY data again. We'll create. We'll check this thing which is part. Say continue. we'll go to this field output. Okay, and then I'll choose this one, which is called N4 score 6. N4 score 6 is nothing but your bending moments, and press apply. Yes, say OK, and then plot. Yes. So this is my bending moment diagram. So the bending moment at the support should be 0. Yeah, it is 0. It started with 0, and you have a sagging bending moment, and then it went like this, and then it became 0 again. So Burhan, how is your bending moment diagram?
It's same, sir, same.
It's similar, right? So what is your, maybe you can check this bending moment at 3 meters. You can, you
67.74.
7.4 something. Okay, maybe at 2 meters. I think, yeah, you can't do. Yeah, for you the mesh size is different, right? Maybe then I think your point will be something different. But anyways, okay, that's okay. What about it's 4500?
Sorry, sir. What about it?
What about your bending moment at 4.5 meters?
2.5. It's 56.99.
Okay. So the reason why I'm actually asking this to Burhan is our results are highly mesh sensitive. Maybe here you are seeing it as a decimal things, but when you have a very minor kind of thing, or a very micro analysis, or a very section kind of an analysis, there it makes a huge impact. So we can also discuss about that, but let me also see what other results we can still plot. Burhan, you can just, maybe this I'll just do it quickly. I'll also tell you later on. So let us say in force score 1 in axial direction. Let us see if there is any forces coming in axial direction or not. See, surprisingly, there is forces coming in axial direction as well. See, it started from almost minus 7 kilonewtons, and then you have drop here and then. See why? Uh, I think Raghu was telling that you will not have any, you might not have any axial forces coming. Right? Okay, so Raghu has a question. So should we keep the mesh size to a lower value to get more accurate values? 300 mm size gives more correct value than 500, which Burhan has considered. See, definitely lower mesh size is gives you more accurate value, because in the real beam, let us say real beam can have infinite number of elements. So definitely yes, the lower one will give. But the problem is if you have smaller mesh size or the lower mesh size, it takes a lot of time to compute. And here there should be a good balance between your computational cost. When I say computational cost, it is the time which you are giving for the problem to solve. Right now for us it's solved in, I think, 5 or 10 seconds, I guess. Even for Burhan it solved it in, I think, not more than 10 or 20 seconds. But for a very let us say if we have a very critical problem or uh, uh, very complex problem, there you need to wait even days, for some days to have the problem solved. So for example, when I'm solving impact kind of a test, it takes almost 3 or 4 hours to solve. So in that case what we need to do is, we can't keep on going for a very finer meshes. So for this, for to understand or to strike that balance between how much mesh size is required for to have an effective computational cost, there is something called mesh convergence studies. We'll do a mesh convergence studies, that we can do it now also, but I think only Burhan is having. But tomorrow, if others are also having, we can also, we can have different groups of people having different mesh sizes, and we can compare these results, and then we can plot. We can also do a mesh convergence with that. Okay. So today we only have 2 points, 2 data points, but I hope you are able to appreciate that even having even for like two data points where I have 300 and Burhan was having 500 mesh size, the deformations are 228 in my case, and in his case it's 226. So there is a slight discrepancy between our results. So if we still have some other data points, we can have some trend happening there. We can see some trend, like as your mesh size is decreasing, your deformations are increasing or decreasing. That's again, we'll discuss when you all guys have this software installed. Maybe in our next class we'll discuss about this mesh convergence. So for now, you just keep this in your mind that mesh, your results are very mesh sensitive. It is sensitive towards your mesh size. See, now you also, like, I just want to highlight this. Here you are also getting the axial forces, right? So from where the axial forces came in, because you are considering your nonlinear geometry here, right? So because of nonlinear geometry, the beam has bent so badly that it also started giving some axial forces into the beam, into the sections. If you remember yesterday, I was I was taking the cantilever beam problem. If you remember, this is my cantilever beam. Initially, you have load which is perpendicular to the beam, but let us say if your beam is bending so badly, okay, then let us say the load is still perpendicular to this part. It will have its components, one in this direction, which is P, and another one, let us say if this is theta, this is going to be P cos theta, and this is P sin theta. Sorry. So in this case, if the beam has very large deformations, this P sin theta term will also give you axial forces. And that's the reason why we are seeing these axial forces in the beam. Okay, so this is one thing which I want to highlight in this. And what is the other one? Yeah, other one is the mesh convergence or the mesh sensitive analysis, which we have seen. Also in visualization, what you can do is you can also, let me go to this visualization scale. So here you can also see here, like, for each loading step. So we have given the step, right? So for each loading, you can see how it is. You can see it right now. You are able to appreciate. So this is my 0 step. That means the loading was not there on the beam. So I'll, like, for sake of Burhan, I'm just repeating it again. Burhan, you can go to this tab over here, frame selector. Select this frame selector. You will see this thing. You
Sir,
can
I'm
see this.
stuck in this diagrams of this.
Okay, you can directly click onto this.
Diagrams.
Yeah, I understand. You directly click this part, this one here.
Okay, sir, I got it.
You got this now?
Yes.
Yeah. Now you go to this frame selector. Now you are able to see this.
Yes. Step one.
So yeah,
Section.
step one. So see, you keep on going to the, so loading started, and it started deforming. You can see the deforming, and then it deformed and deformed and deformed. Okay, so that's how the deformations happened there in the beam. So here you can see for each loading step. For example, let us say now what is your number of steps? You have 15 number of steps, right? So let us
Yes.
say if you have let us say for 20 we have UDL of 20 kilonewton per meter, right? So this 20 kilonewton of meter applies in 15 steps. Like, initially it started with 0, then slowly it started. First one will be 20 by 15, next one will be 20 into 2 by 15, third one will be 20 into 3 by 15, and at the end 15th step it will be 20 into 15 by 15, where you'll have 20 kilonewtons acting. So if you want to see only half, or maybe let us say near to half of the load, so this is, I'm just going to 8 step, and I'll see that at this stage I only applied half of my load, and I can see the results here. Okay. Shall I repeat what I have said? See, what's happening is, now this is my low. This is my load, and this is time or step. You can consider it as step. So right now, what it is doing is it is going linearly. Please assume this as a straight line. Uh, this is your 20 kilonewton. You have this 20 kilonewton per meter, right? So for each step, each step, so slowly it is trying to increase step by step up to this part. And when it is 15th step, for me it is 15th step, it came up to 20 kilonewton. Let us say if you want to see what are your results for 10 kilonewton per meter load, 10 kilonewton per meter load, you can just simply query this step, which is, let us say in our case, maybe 8th step. Or if you want to know what is the load at a very small load of, let's say, 2 kilonewton per meter, then it will be like your step 2 or something. So this can be done. Me, along the loading history, along your loading time, you can also see for different kinds of loads, starting from 0 to the maximum load which you have given. You can also always compare different your uh, your output results in this. And this is one thing. And there is one thing called, you can also have a visualization. See, you can see it right now. You can also see how it is deforming here. So it started with 0, and then it's deforming and it's coming back. It should not come back, but uh, just for creating an animation, it is showing as if it's coming back, but it's a repetition. That's it. It's from 0 to 15. It is repeating multiple times. So this is another. You can animate your results here, and you can see the results over here. And the next one which I wanted to show is, yeah, next one is this. Maybe you can go to this view. Yeah, ODB display options, and you can render beam profiles. Okay, you press this beam profile, you can render it. You can press apply. Yeah, now you can see your beam. See your beam. You can render your beam profile. You can see what's happening here in the beam. And mind you, your sorry, yeah. So this is your beam. Let me take this, or maybe you can also have you. So yeah, this is in this section, like I mentioned, it's a one-dimensional element. So you don't have any along the thickness or along the depth direction. You don't have any variations. It is actually saying that you have same deformations or same stresses in this. Let me also show this. You can also render your section if your section is uh, rectangular, or if your section is a I-beam, you can also get an I-beam, and then you can see how your stresses are varying. This also okay. I'll again repeat. You can go to view, go to ODB display options, general, render beam profile. If you want, you can switch it on. Right now, I just want to switch it off. So apply. Then you'll get back to this line diagram. So yeah, at the end, I just want to save this, save my data. So yeah, I think I'm mostly done I'm done with this example. These are the things which I wanted to show. I'll just check if you guys have posted something. Yeah, this is- yeah. Any doubts so far? So far, like whatever I have covered. Yeah, Maheshwar, I didn't. You said something. Any doubts? Burhan, Raghu, Maheshwar, Vivek, Shivakumar, Deepthi Priya, Abhishek, Jayashree, Madhavi.
Tomorrow class is there, sir. Good evening, sir.
Yeah. I'm.
Tomorrow class. Tomorrow is the online class, sir. Tomorrow is the
Yeah,
fifth
I
class.
think yes. I'll be happy to take the class, but I think I need to check with JP sir. JP sir,
Yeah,
can
yes, sir.
you?
We will have class tomorrow.
Same time.
Yeah, same time. If you want a little early also is fine.
Yeah, see tomorrow maybe we can have one more extra if the students are okay because
Maybe
you
in
know
the morning or afternoon is also fine.
yes.
Hmm?
I'm okay with anything, sir. Tomorrow I'm free.
Okay, I request all the students just you can discuss in the group and we'll finalize the class. Hmm?
Same
Otherwise,
time only better.
hmm?
Same time only better, sir.
Same time, huh? Okay, 7 to 9. So we said 7 to 9 is okay.
Yes, sir. I think it should be fine. But if it is like if I have one more hour, it would be better. That's what I feel. Uh,
Hmm.
need like if all the students are having abacus tomorrow, then it will be more interesting.
Yeah,
So
I request all the students just you download that trial version or
student,
learning version, student version. You have to give your mail ID, you have to create the ID and then you can download that. I mean, you can follow the instructions. So, Buran, is there any difficulties there when you are installing?
No, sir, no difficulties. It was
No
very easy.
difficulty, right? So everybody can download it and you can use it. So whatever the problems we are doing is less than 1,000 nodes only. So it will not be a problem, I think.
yes, sir. We'll try to restrict ourselves to 1,000 points.
Yes, sir. Hmm? So
What?
tomorrow we'll meet at the same time, sir. Hmm?
Sure, sir. I think we can meet
Sir,
at the same time. Others, do you have any questions, queries?
questions,
See,
concerns, queries.
Burhan is the only. I think he's the only person who tried to follow what I've done.
I think
Uh,
Buran is having software, that's why he's following today.
yeah. That's why he's following
So
today.
otherwise, the others also, MTech students also will, maybe
Yes.
tomorrow they will join.
Sure, sir. I also request you whenever you are others, you try to do what we have done for today's class. Once you uh, once you install this student version, and let me know if you have any issues, or let me know if you are getting some error messages. You can post in the group so that others also will learn. Like you know, if that error
Sir,
comes, what
can
to
we
do.
export from stat to abacus, sir?
No,
Stat, no. Stat, see, to export, you need to have some extension files, right? So stat will give you only STD file, right? .std file.
Yes.
So .std doesn't have any export or import option into the abacus. So you can export a drawing file. DWG drawing can be imported into abacus.
From
You can,
AutoCAD we can export.
yes, we can export.
Okay. Thanks.
Yes, yeah. Uh, if you have no doubts, I think shall we end the session for today, or if others?
Okay, producer, thank you very much for the second session. So we'll close this for today, and with one more problem, we'll meet again tomorrow
Sure.
evening, same time.
Sure. One more thing, actually, I forgot. I need to send a feedback form also. Let me just share it again, because this is a first hands-on session, right? I just want to see what. See, yesterday's feedback was. See, I thought there will be some critical feedback, but I don't know. I didn't get any critical feedback. I don't think that I'm doing a very great job because I thought you'll be giving some critical feedback. Only one feedback which I got is the writing was not so good. You're not able to follow my writing. So I tried to change today. I think it is okay, I guess. But yeah, so please try to give some critical feedback so that uh, so that I can try to improve. Or if you're not able to follow, we can also discuss, and it can be more effective. That's what I feel. You can, yeah, I just messaged in the group. You can click on the link and give your feedback. Then we can move on. So this feedback will be for this one, and at the last I'll have another feedback. So meanwhile, I'll not keep on asking you for the feedback, because this is my first hands-on session. That's why I just wanted to have. I just wanted you to give me some feedback. Okay, then I think that's all from my side for today. We'll meet tomorrow again.
Hello, Prithvi, sir.
Yes, ma'am.
Yeah, I really thanks, sir. You're explaining everything in detail. Can I have JP sir here?
Yes, ma'am.
Sir, is it possible to share today's video in Google Drive so that tomorrow whoever installs it, at least look back the
They can
details?
practice.
Yeah, because all of a sudden if they install tomorrow and Sir Prithvi wanted to explain the second problem, again he has to tell all the basics. So I think whoever is on track will get diverted. So I don't know, I just thought of, what do you say, sir?
No,
Yeah,
that's a
sure,
very
ma'am.
good idea.
I will share the link.
Yeah. Yeah, thank you, Prithvi. Thank you so much. And I would like to, in this platform, I would like to, appreciate Burhan. You know, being a BTech student, you are following the things and you are so interested in learning things. I request all the MTech students, because this is specially for the MTech students, so that you can, take help of this and incorporate the things in your project work, so that you can get a paper published. So I request all the MTech students to install it today itself. Okay, and as sir said, he'll be uploading the video in the Google Drive. Take some time and try to practice it and get ready for tomorrow's second problem. This is my request to all the MTech students. Hope it is okay, Prithvi and JP sir.
Yes,
Yes,
yeah,
ma'am.
yeah.
Thank you.
Yeah, yeah. Thank you, sir. Thank you.
All right, yeah. Thank you. Bye. Good night.
Bye. Good night.